The presentation today is titled Visualizing Job Usage with the ViewClust Python package. This presentation, part of the general interest webinar series that we have at Sharcnet, is really an update on presentations that we've done in the past about how utilization is tracked and affects wait times on the scheduler. We also did a summer school workshop on this sort of thing. One of the issues that commonly comes up is what resources are made available to researchers in order to actively be able to explore and visualize their usage on the system. So what we've done, and particularly with the help of my colleagues, Tyler Collins is here, is we've made available a Python package that we call ViewClust. And what this does is allows you to build these interactive figures. So this presentation is about what aspects of job usage are important to track, and then a demonstration of how to use this Python package that we're developing to help you assess work. Again, my name is James Desjardins. I'm one of the analysts with Sharcnet. My office is at Brock University. So the overview of this presentation is really to describe the factors that affect wait times in the queue of Compute Canada general purpose clusters, specifically the Graham, Cedar, and Beluga systems. And importantly, what we want to get across is that these are the general purpose systems are very heterogeneous. They expect all kinds of different workloads, but another very important property of them is that they are completely saturated. That is, there aren't resources that are just waiting idle unless there's a specific reason for those resources to be idle. The load in the queue of these systems is always saturated. There's always work waiting to run. So the scheduler has to make decisions about which jobs run when. And what we want to get across is the importance of priority in this. So the next thing is that because wait times are necessary, usage decisions that can lead to unnecessarily long wait times in the queue are important to be able to identify. So one of the aspects of working on these general purpose systems that are very heavily saturated is that the wait time that a job is in the queue can be a substantial part of the time to results for this work. So understanding the way that jobs are triaged and then being able to assess your specific workload can go a long way to improving your time to result. So what we want to be able to do is query properties of the system, the scheduler, and the job queue. And in particular, in this presentation, we want to be able to do the visualizing of the job records with the ViewClust Biz Python package. So what are the main factors that affect wait times? So the resources on the cluster, there's a limited number of resources, and then there's the resource requests, which are the jobs. The jobs wait because there aren't enough resources to handle all the jobs at any time. And wait time is the only tool that the scheduler has to distribute workloads fairly. And we're going to go into all of the factors that affect that. So the resources are cores, GPUs, and memory, etc. There's also things like software licenses and other things we won't get into. The ordering of the jobs in the scheduling queue is done by priority. So this ordering of the jobs is really what we want to be able to assess by looking at the job records of an account. The factors that affect the ordering of the queue or the priority are the target share of an account. That's the expected throughput trajectory of any one account, the recent usage, and particularly the core equivalent measurement of the recent usage, which is something that can be a bit deceiving and unexpected sometimes. We'll make sure to cover that specifically. Now, finally, the other major factor is the scheduler configuration. In particular, because the general purpose systems are intended to handle pretty much any sort of workload that researchers have, from serial farming to large-scale parallel processing, the system configuration has properties that affect the start time of the jobs. This is mostly implemented through partitions on the general purpose systems. And partitions basically make specific resource requests that are isolated to a subset of nodes. So for example, we do allow 28-day jobs to be submitted to the system, but they're only able to run on a very small set of nodes. And this partitioning can really affect the wait time of jobs. So here's some usage decisions that can lead to unnecessarily long wait times. Memory requests are a huge factor in the wait times of a job, particularly whenever you make node requests that isolate your job to very small subsets of nodes on the system. And this can happen both because of partitioning, but also because of the actual hardware that's available on nodes. For example, we have hundreds of nodes with 128 gigs of memory, but very few with 256 gigs. If you're submitting jobs that trigger the requirement of 256 gigs, your wait times are likely going to go up. There are the partition constraints, which I mentioned previously, and we'll go over the layout of that. Another thing is whenever you're submitting heterogeneous jobs from a single account. We'll go over this briefly. Basically, some jobs are very easy to fill. They can fill in gaps even if your account is at low priority. But if your account is doing that, it will be very hard for that account to also run difficult to schedule jobs on the same system. And then finally, the recent usage of an account contributes towards the fair share and then hence the priority order of the jobs. So it's important to understand how the jobs are actually billed towards the fair share. And core equivalence is an important part of that, where the amount of memory that you're requesting is integrated into how much a job is billed. So there's different things that you can query on the systems whenever trying to understand or predict either predict wait times or modify expectations of throughput. So you can check what the resources are, what's available in the system with commands like sinfo to the scheduler. There's also a command that was made called partition stats, which gives a snapshot that doesn't fully recognize some of the complexities of the system, but will give you sort of a large overview snapshot of how many jobs are running on the system and what the partitioning configuration looks like. So how are nodes organized in partitions, so you can see the specific configuration by calling commands like scontrol show partitions, which will give you the layout of all the partitions in the system. You can query things like the job load in the queue and what's running on the nodes with commands like sq and sacct for saccount. And then finally, we really want to get into the summary of an account's job records with the ViewClust Viz package. So let's just give a quick rundown review of how jobs are actually scheduled on a system. So the cluster is made up of nodes. Those nodes have a certain number of cores and a certain amount of memory, and they're operating over time. So in this case, we have cores along the x-axis, and we have memory over on the side there. And then up the y is basically time. So each one of those cells over here is a single core. There are 10 cores on this node, and then there's an amount of memory that's available to these cores. And then this is considered 1 hour on this plot. So what happens is over time, the scheduler is going to try and fill up this node. At the first scheduling cycle, it will check the queue and see what it can fit in there, and then it will basically go up through the queue and try and fill the node. So here's an example of this single node, a simple example of what the scheduler would have done as it passes through the queue. So let's take a look over on the right here. We have the job size and the actual definition of the first job at the top of the queue. It's looking to run a job for 1 hour with 1 gig of memory. We see that this job ends up going into the system right now, right here. And then what it does is it just goes through the rest of them. Now the second job in the queue is asking for 6 hours and 8 gigs of memory, and then 8 cores. We see that it ends up taking this big space on the system, but it is able to start right now for this period on this cycle. And then we also see that it takes up the rest of the memory on this node. So at this point, during this scheduling cycle, this node is what we call saturated. There is no more memory left for any more jobs to run, even though there's a single core that's still idle. So although there are idle resources at this time, the node is currently saturated because all of the memory is being requested. So the next job that's submitted here is a single core job requesting 2 hours and 9 gigs of memory. Although at this time there is the single core available down here, because there's no memory available, this job cannot be scheduled until after the 8 gig job runs. All the while there being plenty of cores, but not enough memory to run that job. And then finally, we have another, there is a single hour job on a single node requesting 10 cores. And then we see that job can only run after that single core job over here. So at this time, this is something like 10 hours later, all of the jobs in this queue have been able to run. Some of them being able to run at the same time as others, but others having to run alone, saturating the system. Now, what we want to get across here is that whenever we're charging for the usage of a system, we aren't just charging for the number of cores. For example, the first job in this list is a single core job, and the equivalent charge is still 1 core because it's requesting 1 core and the equivalent amount of memory. So it's basically, in this example, it's 1 gig of memory. The second job is requesting 8 cores and is charged 8 core equivalents. There's another big parallel job here that goes across nodes and is only requesting a little bit of memory per. It's charged 10. But the important one to note here is this job that's charged 9 core equivalents. This job is the one that's right here. It's only using a single core for the entire duration, but because it's using the equivalent of 90% of the node in terms of its memory, it's charged 9 core equivalents. So this is an important part of how to assess the utilization that is billed to interpret the priority of subsequent jobs for an account. In this example, although the initial thought is that this is just a single core job, and for its duration, it would only be getting billed a single core, it's actually billed what's called 9 core equivalents. And then the final job with the 10 cores, it's using 10 cores, but only half the memory. It's still being billed 10 core equivalents, which is basically the largest of the resource dimensions of the job. Okay, so here's how the actual ordering of this happens. Let's say we have the fair share priority queuing. We have an example of 10 accounts with equal shares in the system. So we have accounts 1 through 10. They all have basically an equal target share of the system, and let's say they all submit jobs during the first cycle. All of those accounts get one job running on the first cycle. They're all equal. So in this case, it's kind of like the first in, first out. All the accounts submit a job, they all run a job, and then on the next scheduling cycle, if the first account submits 2 jobs here, and the second account submits 2 jobs, but accounts 3 and 4 don't submit any, then accounts 1 and 2 on the second cycle will be using twice their share of the system during this second scheduling cycle. Now, what that results in on the next cycle is if all of the accounts each submit 1 job again, the priority of accounts 3 and 4 will be higher than the priority of accounts 1 and 2, because accounts 1 and 2 are now beyond their fair share of the system, which is basically 1 core per cycle, and accounts 3 and 4 are now below their fair share of the system, which is 1 core per cycle. So now, whenever the scheduler is going through the queue trying to place things, accounts 3 and 4 will be the first in the queue. And this is basically how the entire thing works, where there are constantly jobs coming in from all of these accounts. There's certain resources that are coming available and then getting used, and the scheduler is interpreting the jobs based on the priority, the fair share priority of the accounts, and then it just goes through the queue like this. So the fair share target. So in a production, the target shares are not all equal. So this is where we get into the resource allocations on the Compute Canada systems. We have the RRG and the RPP accounts that have a defined and unique target share of the system. And then there's the RAS accounts, or the Rapid Access Service, which is basically an equal sharing of whatever is left over on the system. So in this way, accounts basically have a target share of the system. The target share of the system is basically what we want to compare an account's actual usage to. We'll take a look at that in a bit. Now, the other thing is, so far we've just been looking at a single node and how it populates, but the general purpose systems are many, many nodes. So if we take the single node view that we were looking at and then put it into one little box in the node, in the cluster, then we see that there are actually several different groups of nodes that are allowed to do different things. In this case, the partitions restrict jobs of specific shapes to certain node sets. So jobs that are requesting full nodes can run on most any node. These are called the by-node partition. Jobs that are 24 hours and shorter can run on most any node. Longer runtime jobs have access to fewer nodes. So for example, all of the nodes on the system that we're looking at here can run these one-day jobs. But if you're running 28-day jobs, you're going to be restricted to a very small set of the nodes on here, which can have a significant impact on wait time. So partial node jobs, these are jobs that are only using some of the cores on the system or distributing across nodes and only using some of them, have access to fewer resources than the by node. As well, there are backfill jobs that can run on most any nodes. So once the scheduler goes through a cycle, it looks for resources that are still available and will try and fit small jobs. So in the partitions, we see a main distinction in the by node versus by core. So by node jobs can perform better sometimes because they aren't doing the between node communication, but by core jobs have more opportunity to run. So in this case, we see that the blue job, which takes up a full node, requires an entire node to be idle at the time, whereas a by-core job, even though it's the same size, the same number of cores, has to be distributed across a whole bunch of different nodes taking up. So these jobs can find gaps on the system and are easier to schedule. So the partitioning tries to favor the by-node jobs. Okay, so here's where we get into understanding the key measurements that we want to be able to do with our accounts in order to interpret how our recent usage of an account is going to affect our priority on the system. These are the visualizations that are made by the ViewClust package. So this figure is the job stack figure that's created and made available by the ViewClust package. In this figure, each job is represented as a rectangular object. The x-axis is the date time. So basically over the duration of a query of the system, you'll see this. And then the y-axis is the cumulative resources that were requested by all the jobs. So for example, this rectangular object here, so this rectangular object here is the first job. It had a time when it was submitted, which is here. It had a time when it started running, which is here, and it had a time when it ended, which is here. This time over here is the actual requested time from the start of the job. So if we want to be measuring the utilization of an account, we basically have to look at all of these job records and then tally up the height of these jobs over the duration of the query that we make. So if we take a bit closer look, we see that the first job was queued, what's that, on March 25th, 2019. It has a start time. The gray area then is the queue time of this job. It also has the requested wall time expiry. And then we see that it actually ends before that time. And then this duration from the start of the green to the end of light blue is the total wall time requested, which in this case was 8 days. Now, the actual endpoint is all that this job is actually billed for. It doesn't actually bill until the end of the requested time. It stops billing towards fair share at the end of the run of this job. If this job runs until the end of the requested time, it's killed prematurely. Now, what we want to be able to do is then measure how many resources we're running at that one time. So for example, this first job, the requested or considered used is about 220 core equivalents. And then we see that jobs have different heights based on how many resources they were actually using. Now it says here cores, but it actually takes into consideration the amount of memory that was used in that as well. So in this case, job 1, this is the area that the resource requested by the allocation. And then for job 3, this is the area that it actually used. Now, importantly, for these figures, what we don't have access to right now is that inside of this job, it may have only been using, let's say, this many cores or this much memory. What's important to notice at this point is that even if this job was only using, what's that, like a quarter of the memory, it's actually billed for the entire request during the period that it runs. So in this case, if you're requesting 4 times as much memory as you actually require, your account will be billed 4 times as much potentially as you actually need. If jobs are billed 4 times as much, it means that the fair share prioritizing of these jobs will be limited to a quarter of your potential throughput. And this is why the usage request can have a substantial impact on the total throughput of an account. All right, so here we're looking at sort of a step back and seeing more of the jobs of a specific account. Now they're all stacked one on top of the other so that we can see them. And then we see here, this is actually like a full-on view of a long duration where an account was submitting jobs, they were running. And then, we see here there was an actual issue where there are jobs with a very long wait time for some reason. This is the kind of situation that often triggers a ticket to the Compute Canada ticketing system. And then what I would do is I would go through and generate these figures and then work through what exactly was happening with these specific jobs. What we want to do in this presentation is make it so that users themselves can now generate these figures on the systems. Okay, so this is now the summary of the measurements taken from those job stack plots. In this case, the gray area, this line right here, corresponds to the account's target of the system. This area is basically the throughput that the scheduler is trying to maintain for this specific account. In this case, what is it? It's something like 600 core equivalents. Now, the next thing that we see is the dark blue line. The dark blue line that goes like this is basically a sum at every time point of the running resources. So that is the green rectangles in the job stack plot. This is the usage that the scheduler is using to determine the account's fair share of the system. So over this period over here, the usage of the account is above its target, which means that the priority of this account is going to decrease after this. Over during another period, the usage of the account is below the target, so the priority of this account will go up to try and keep this account fluctuating around the target share of the system. Now, what we see in a situation like this is really what we want to be able to assess whenever there is a wait time that we want to diagnose. This light blue line is the sum of the resources waiting in the queue. That is, it's the sum of the height of the gray boxes in the job stack plot. When the amount of resources that are queued is large and above the target, but the actual usage of the account stays low, this is a problem that we want to try and diagnose. And it's easiest identified using these specific figures. Now, the other thing is then taking those plots and just plotting them as a cumulative sum. In this case, the gray diagonal line is the target trajectory of the account over time for how much usage it should accumulate over the duration of the query. And then we see the blue line is trying to keep on that trajectory. The scheduler allows it to go beyond its target during some periods, which is great. But here we notice a problem where there's a bunch of resources queued and trying to run, but the slope of the usage line isn't keeping up with the slope of the target trajectory. This is when we know that we've identified a problem that we would like to clear up on the system. And this can be for many reasons. So, what do we want to do? We can go in right away, and we've talked about this a few times. We can do things like show all the jobs in the queue sorted by their current priority. This will basically give us a list of where a specific job is as it's being interpreted by the queue to be dispatched to a compute node. This is the exact command you can use to do that here. So on a system, this will print out all of the pending jobs sorted by their priority, and then it'll give a bunch of the details of it. And then you can use this to see where your job is sitting in the queue. If for some reason it's still very low in the queue, which can certainly happen if a bunch of new high priority jobs enter, then that is an important part of the interpretation. You can show properties of all the jobs for specified count on the system since stated date. So in this case, I'm going to use something like sacct, showing all of the jobs, and just the capital X just means only show the batch step for a specified account over a duration of time. And then we can list a bunch of the parameters, for example, the account, which partitions they're trying to run in or running in, the submit time, the start time, the time limit, the requested memory, the number of CPUs, number of nodes, and the state. A lot of these parameters are the ones that we use when building the figures. And these are the things that are interpreted in the ViewClust package. We can also show node properties. So the node properties, understanding how many nodes have a certain amount of memory, for example, is important, using the sinfo command. And then showing partition properties. So a command is made available called partition stats on the system, which give a table layout of how many nodes and resources, as well as jobs are present as a snapshot in each of the partitions. Or you can use control show partitions to get the actual definitions of all the partitions on the system. Now, what we want to do right now is go onto a system and actually run this summary, creating the job stack plot and the utilization of the system. So what I'm going to do as an example is I'm going to log into a system. I'm going to create a new working directory, go into it, and then following the instructions for Python on the Compute Canada systems, I'm going to load the Python module as appropriate, create a virtual environment, source the virtual environment, and then finally I'm going to do the pip install of the ViewClust viz package on the system. And then this will allow me to create these multiple figures for an account on the system. Finally, all we have to do to run a summary is start the Python interpreter, and I'll just be using a login node for now. In the interpreter, import the ViewClust viz package, and then I'm going to run this command here called the show job use. Now, there are various tools inside of the package for building data frames in Python of the job records. The specific one in ViewClust viz, the show job use, builds all the summaries that we've been talking about so far. So actually, what I'm going to do right now is I'm just going to go over to a system and go through this specific example before we go through the rest of the presentation. So here I am in a local terminal. And then what I'm going to do is I'm actually going to log into the Cedar system, where I've recently had to work on a MATLAB project. So I was using the MATLAB license there. So I'm just going to, let's see here. So I'll just log into Cedar. And then what I'm going to do is I'm just going to set up the entire environment that I just talked about. So if I LXL here, got a few folders, and then what I'm actually going to do is I'm just going to create a new directory called job measure. CD into job measure, and then this is currently empty, which is totally fine. And then really just following the documentation from the Compute Canada wiki for Python, I'm just going to get my module for load Python, check them. So I've got my, and then the same thing, I'm going to create a virtual environment here. And that's also the Python wiki for Compute Canada. And then I'm just going to go ahead and source that environment. Okay, so now that we have this new environment, virtual environment for Python already, now I'm just going to go ahead and I'm going to install the ViewClust Viz package using pip install ViewClust Viz, and then we'll just wait for this to happen. Okay, so here we go. It's installing ViewClust Viz as well as its dependencies for doing all the work that we're going to want it to do. Now, while this is happening, I'm actually going to just start another terminal here. And I'm going to get ready to explore the figures that those tools will make. So what happens whenever we run these figures is it generates a set of HTML interactive figures. So I don't want to be actually viewing them in the login node over there. I want to actually view them from my local computer. So what am I going to do? What I'm going to do is create a SSHFS mount for the drive on Cedar. My goodness. So here I'm just doing the secure shell file system, me, jdesjard at cedar.computecana.ca, and I'm just going to mount my home directory into this empty directory that I have on my computer here. And what this will do is it will allow me to explore the files in that directory, my home directory on Cedar, from my local machine. So what I can do now is I can say ls temp mount Cedar, and then I can see my home directory there, and then I can actually go into the job measure where I see that I've created my virtual environment. So now here on my local machine, I can then explore that directory using all of my local software. So here we can take another look at it in my file browser, where I'm currently pointed into my temporary mount Cedar, and then in my job measure folder, and then I can use my local file browser to then explore the files that are in there. Now, okay, so I go back to my terminal. It's successfully installed ViewClust Viz and all the dependencies, and now I'm basically ready to run this. So what we do now that I'm in the system, I've created my virtual environment, I've sourced it. In this virtual environment, I've installed ViewClust Viz. I can then start up the Python interpreter. Now in Python, what I want to do is I want to import the ViewClust Viz package. So I'm going to import ViewClust Viz as VCV. And so far, so good. Okay, so now in my Python interpreter, I can start running the commands that are made available. You can kind of go over a view of all the things that are available at the Git repo. And then here we have the VCV, show job use. What I'm going to do is I'm going to run a query on my default account for CPU. The second input is the target shares of the system. So basically the estimated throughput that I would expect for this account. The start time of the query that I want to run. So I basically want to see everything since the beginning of July. And then I give it an output path for the figures that I'm generating. And then I'm going to specify a couple of the non-default figures. So there's a figure called the plot memory delta. This will show me the difference between the memory that I requested and the maximum pulled memory inside of a job. And then I'll also plot a scatter plot that will show me the relationship between when a job started and what the wait time was, which will be categorized by the partitions. So I'll hit enter, and then it goes through, spits out a couple things. In particular, this is a small query where there was only 38 jobs submitted to this account. So the reason I'm taking a look at this one is I had a deadline for an analysis a few weeks ago, and I had to script a bunch of things to run in MATLAB on the system. So there's a few jobs that had to run within a certain amount of time. So let's take a look now at what actually got generated. So if I'm take a look at the folder, this job measure folder, and I refresh it, I see now that there's this usage figs folder. Inside the usage figs folder, I have these standardized names, HTML files. One of them is the job stack. There's the instaplot, cumulative plot, and then the other two default plots that I requested. So on my local computer, now mounted here, what I can do is I can just double click, take a look at the job stack first. And what this will do is it will open that figure in my default web browser. And that figure looks like this. So this is the job stack figure, where each job, if I hover over, I get the job ID, so I can then go and look at the specific details in there. For all of them, I can also zoom in. So I did a bunch of testing to try and get this optimized properly. And then near the end of the deadline, I did a little production run here. I can see the time it was submitted, the time that it started, each of the jobs, and then the time that it ended versus the total amount of time that I requested. So I can see all of these for the periods. Now, what I'm really interested in a lot of the time when I'm trying to assess the priority of how this work would have affected my subsequent wait times is really the sum of all these green areas at any time. And importantly, the size, the height of these jobs is affected both by the number of cores and the amount of memory that I requested at each time. The actual timeline over the duration of the query, that is the sum of these, is called the instaplot. And that is the instaplot right here. If I double click on that one, I see the actual timeline of the usage for this. And we see here that the scheduler for this account is trying to maintain 50 cores over the period. And this is typical of default accounts. But at the maximum time during that last burst of usage around July 5th, I only ever got as high as 17 cores or core equivalents. So this account is still considered below its target share of the system and is likely to still have a high priority. Now, the color area under here is actually indicative of which users were submitting the job, and there's a bunch of other details that are available there. Now, some other figures that are important to note are the memory deltas. So the memory delta plot can be an important part of how we assess jobs. This figure, each green dot is actually the measurement of how much memory was used during the running of each job. Now, it's measured as the peak pooled memory during the job. So it may have only happened for an instant, and that measure may have actually missed the true maximum peak. But what we see here is early on with these MATLAB jobs, we often start overestimating the memory. We ran into some problems, so getting a segfault issue, I increased the memory even up to 16 gigs, but it was only ever using, looks like about 1 gig at that time. And then I started dropping the amount of requested memory, which is the red dot, that's the requested amount of memory, and trying to adapt to how much memory was actually being used until I settled on basically the 4 gig, which is a typical core equivalent memory. So there's typically 4 gigs available to every core. And then we ran it that way, seeing that the memory would go up to almost 3 gigs per job. Another thing that we can look at once we have these job records in Python is we can start to compare different aspects of the job. For example, this figure is plotting the start time of the job and then how long it waited. So the y-axis is now the wait time in hours. So the job that waited the longest is somewhere over here, and then when it actually started. This one is now coloring everything based on which partition the job actually ran in. So we see here that a few of my initial jobs actually ran in the interactive partition. So I was interactively logging in and trying to run these jobs, asking for resources, and those pretty much start right away. The system is set up to favor that interactive jobs can start without delay, which is an important part of the debugging process. And then later, whenever I got into the actual production, I was submitting jobs with up to 16 gigs, which actually triggered some of these jobs to go into a different partition, although they all started very quickly. So here in this slide, we basically just go over the example of how to view the data once we've created them using the ViewClust package. Basically, typically just mount the drive on the remote system into our local drive, and then from a typical file browser or whatever software we want, we can then visually explore and interact with the figures using our local software. So some of the relevant online resources for doing this sort of stuff, always, understanding the way that the Slurm scheduler works is important. And you can just see the documentation for it here. For Compute Canada specifically, you can get information about how to run jobs at the running jobs page. The policies really define how priority is set. This describes the actual allocation process and what it means to have an allocation and a specific target share of the system. Then getting information about the general purpose systems. So at each of the system pages, you can see what types of nodes are available and what the constraints are for running different types of jobs. For example, if you need 200 gigs of memory per node, how many nodes will that restrict you to? And you can find all of those details on the wiki pages for each in the system. Specifically, if you're using the ViewClust package, you can also get the information on how to run Python right on the system itself to generate these usage summaries. For ViewClust specifically, visit the GitHub repositories. So ViewClust Viz are the actual plotting tools, which uses the backbone of ViewClust. ViewClust is able to generate the data frames that are required to calculate all of the usage measures, whereas ViewClust itself is really about rendering the figures and making them available in an interactive way. So really at the end of the day, this comes down to what can be done about wait times. So understanding the node memory limits and understanding that the node and partition memory constraints really impact usage. And it's important to be able to examine how much memory is actually being used by your jobs when you run them, not just continue to increase the memory and until you're having more memory errors, but actually being able to visualize what your memory usage is as the population of your jobs from an account. So understanding that if jobs are ending up in different partitions, this is going to seriously affect the number of resources that are available for the job. So understanding what job parameters will change the partitions that you end up are important, and then actually being able to visualize if specific jobs that end up in different partitions end up having longer wait times, or what those relationships are. Whenever an account has heterogeneous workloads, it can become complicated. If one user is submitting cycle scavenging where they can submit thousands of jobs and they all find little cracks in the system, this will affect the priority of the entire account. And then other jobs by other users that require high priority to run, for example, large memory jobs or long runtime jobs, those won't be able to run easily. And then it'll be a matter of our recommendation is to work across the various systems, as the billing is completely independent on each of the general purpose systems. And then always recognize that the memory requests of jobs, regardless of how much is actually used inside of the job, the memory request of a job not only determines how difficult it is to schedule that job, because the footprint changes sizes, but it's also a primary factor in how much that job is billed towards future priority of other jobs. So decreasing the job footprint is always very important. And the only way to do that is to kind of be able to see what resources are actually required from the job. In the job stack plot, we can visualize every job, how much time it actually used compared to how much it requested. And then in the memory delta plot, we can look at how much memory was requested versus what the peak memory that was actually pulled during the running of the job was. And considering those two plots whenever sort of adjusting future job submissions is probably the most important part of submitting large scales of production work on these heavily saturated general purpose systems. Of course, we also need to understand the load on the system. There are a lot of users, and we can examine the queue for where there might be sort of an abundant load on the system, and you can work across systems anytime. And then understanding the usage relative to the target share and the fair share priority. If you find that the default usage, which is, we typically estimated about 50 core throughput over the duration isn't enough, then we recommend applying for a resource allocation. So in conclusion, the scheduling policy is prioritizing account targets, consumption, and system utilization. Job submissions should always prioritize the optimal running of the procedure. So doing profiling and understanding what's being used inside of your jobs, and then being able to summarize and visualize the population of your jobs is an important part of this. But also submit jobs based on the feasibility within the scheduling policy. So trying to pile massive amounts of memory into a job whenever you could be doing it with less memory better fits the way that the system is able to schedule jobs. Also, being able to visualize these jobs with ViewClust is an important way of profiling quickly and optimizing your submission behavior. Of course, submission behavior is a very important part of determining your time to result, and do not hesitate to open support tickets regarding the job shape and queue properties by emailing us at support.computecanada.ca. This is actually a very important part of the support that we provide in determining ideal job submission behavior. So that's the end of the presentation. Thank you for your attention, and we have time for questions, and I can stick around for a while.